first lesson about minerals, we discussed how minerals had to meet 5 criteria. Quickly, we discussed they have to be a solid, they need to be inorganic, they need to be naturally occurring, they have to have a definite chemical composition, and they have a regular 3-dimensional arrangement. When we look at these more in depth, we will see that these 2 last ones right here are pretty similar, that the chemistry of a mineral actually makes up its arrangement or its crystal structure. And there's 2 ways in which we can see 2 properties that we can really look at about minerals that deal with their chemical composition. But first of all, what's going on in a chemical composition? The chemistry of minerals. Basically, chemistry, we look at ions. And ions are atoms that have an electric charge to them because one or more electron has been removed or added to the atom, okay? So for example, if I just have plain sodium, which is Na, okay, it's plain, it's sitting there. Generally, sodium likes to have an electron removed, okay? So if I remove an electron, I'm going to get something called Na+. Na+ means that an electron has been removed from sodium, and now this is an ion. Ions in minerals are packed together very tightly in an arrangement. They go close together, and they usually are positively charged, are going to be close to negatively charged. So we know that opposites like to attract. So we know that positive charge likes to go with negative charge. Okay? This kind of this opposite charge of each other, so positive next to negatives, keeps the mineral together as a solid. And so we generally will see that as this kind of cube-like structure. So we can see that we have some different ions put together next to other ones. This might be a positive and that might be a negative ion, which means that this element right here is going to give an electron over here, and all is happy and all is good. So this chemistry of minerals, this fact that we have ions, really helps us to start getting this to maintain that a mineral is a solid, and we know that minerals being a solid is one of the 5 criteria for them. Now, I've been talking about the removal of an electron or the gaining of an electron to give us this structure right here. Just to refresh your memory, if you did not already know, electrons are particles with a negative charge to them, which orbit around the nucleus of the atom. Okay, so if I look at this picture right over here, you'll see that this picture we have inside here, we have positive charges, and these dots right up in here are the electrons. And electrons generally float around if we really look inside the structure of an atom. Again, I'm hoping that this portion right here about electrons is a nice review for you and that you've seen this already. Now we have ores, and ores are rocks that contain valuable minerals, and they can be mined or blasted out to get them. So for example, we have oxides and sulfides, silicates and coppers. This right here is used for glass, so like our windows especially. Okay? And then we have rocks. And rocks are naturally occurring aggregates of mineral grains. So here's my little picture of rocks with their little faces on them. The chemistry of minerals, the fact that we have these ions that are making this nice solid structure for us, the arrangement of these ions is going to play a key role for us in 2 properties of minerals. One of these properties being cleavage. Okay? Cleavage is the breaking of a mineral along a regular orientated plane of weakness, thus reflecting a crystal structure. So when we can see a crystal with our naked eye, basically the way a mineral is going to break helps us to understand possible elements that are in this structure. If we look at this picture right here, cleavage is happening along this way. So when this rock is broken, this rock will break in a long pattern, and so the crystal structures are going in a long direction. And that gives us maybe an idea that the crystals then, instead of being placed like this to each other, they're more placed up and down from each other, making more like long chains together. Okay? We are going to look at cleavage when we break some rocks in class. Now, another thing that makes us have another property of minerals that deals with chemistry is the crystal shapes. Crystal shapes, when minerals grow in an unconfined space, so meaning that there's no limit to how large they can get, they will usually develop a crystal shape that's unique to that mineral and unique to the elements that are in that mineral. I would like, for example, if we look right here at quartz, quartz is right there in that picture. Quartz is a six-sided column with pointed tops to them. So crystals of quartz generally grow in these nice long shapes, right, kind of one right on top of each other, here and here and here and here. Granites, on the other hand, will grow in a 12-sided shape. Okay, and there is granite or a garnet right there, and they tend to grow in a crystal structure similar to that, and they grow all on top of each other like this, giving us this nice piece of mineral. I'm going to show you a quick YouTube of somebody else explaining to you guys crystal shape. You do have some questions regarding this, right along in your notes.
That changed my life forever.
Sorry about the advertisement. We all know Google likes to advertise now.
A crystal is a solid example of a mineral that has flat surfaces as these regular minerals. Now, if you look at a typical rock specimen like granite, for example, you can see minerals in it, but they may or may not be beautiful, well-formed crystals. In order to have crystals that are spectacular, like this specimen of fluorite here, you have to have certain conditions that are met. The first thing to remember is that crystal formation is very, very slow. You have to have a geologic process that allows time for crystals to develop. And then secondly, you have to have room for it to grow. In other words, fluorite crystals here did not develop inside the solid mass of rock. It was a little cavity, probably filled with liquid. Gradual precipitation, which means forming solids from liquid flakes. Now, there are three specific ways or places where we get crystal formation. One of them is exemplified by the granite we looked at just a moment ago. Granite forms from molten rock, which we term magma, and as that moves very slowly and gradually, you start to get individual crystals. And they reach a size that makes them big enough to be seen with the naked eye, but because it's the molten mass, they all sort of interpenetrate and you go through real spectacular, well-formed crystals. Although in some cases, if you have a cavity or an opening that can fill with gas, for example, or liquid, that might take place. A second way in which crystals form is from precipitation in liquid, as we've already mentioned. Fluorite a moment ago. Here's another example, rock salt. Look at the oceans of Europe, about 3.5% of the oceans by mass salt is one, and high concentrations of that normally will be caused by evaporation of water in hot, dry areas. You will get evaporites produced at this rock salt. Look at it closely. You can see the perfect example of salt crystals. Some of these have real nice crystals. The other way in which crystals form, I don't have a fancy example here, but what they're called familiar with, it happens inside clouds when you have the condensation of moisture in the atmosphere and the production of snowflakes. So every time snow